So the next series of videos is going to focus on linear inequalities in two variables. So we have to merge kind of two worlds. So you do need to kind of go back to linear inequalities in one variable, okay? So we would have something like x is less than 6. Well, that would tell me that if I was solving an equation or solving rather an inequality in one variable, let's say the variable was x, all the values for x that were less than 6, not including exactly 6, would be part of the solution set. So I would draw a number line. I would locate my endpoint, which would be 6. I would put either an open circle or a rounded bracket at 6. And then I would shade to the left to indicate to the reader that everything to the left of 6, not including exactly 6, would be part of my solution set. Similarly, we could have had something like x is greater than or equal to, I don't know, -3, doesn't matter. All right. This would say if I was solving a linear inequality in x, just the one variable, and I got to the point where x was greater than or equal to -3, that would tell me that my values for x would have to be 3, or -3 rather, and anything bigger than that. So I would draw a number line. I would locate my endpoint of -3. I would use either a closed circle or a square bracket on -3. That tells the reader I can include the -3, and then anything to the right of that would be part of my solution. So what we're going to look at in this series of videos is how do we take that world, that idea of linear inequalities, but bring it into this two-dimensional space that we're solving these now linear inequalities in two variables. So we have to take this idea of linear equations in two variables and merge it with this idea of linear inequalities in one variable and see how that's going to apply now, okay? So topic one, we're going to start pretty easy. We're just looking at solutions to linear inequalities in two variables. So got a couple of definitions. A linear inequality in two variables is any inequality of the form ax plus by is less than c. We have a few conditions, well, a couple of conditions really. A, B, and C are real numbers, decimals, integers, positive, negative, fractions, whatever. The only condition there is that A and B cannot both be 0 at the same time. So essentially, you're just taking standard form of an equation, but you're replacing that equal sign with an inequality symbol. And I want to be really clear. Any of the four inequality symbols work. We could use less than, greater than, less than or equal, or greater than or equal, okay? Now, a solution, we're going to have to talk a little bit more about solutions in a moment when you actually see the graphs here. But the solution to a linear inequality in two variables, x and y, is an ordered pair of real numbers such that when the x-coordinate and y-coordinate are substituted into the inequality for x and y, we obtain a true statement. So again, our solution is going to be this set of ordered pairs. And the way we're going to kind of merge that with this idea of inequalities is we have the actual line. The line is kind of like the boundary point, except instead of being a single point, it's like a boundary line. That splits the Cartesian plane into two regions called half planes. We either include the points on the line or not, and then we include one of those half planes. So it's going to be this cool merging of these two things that we already know. But for now, we just want to know how to test a single ordered pair to see if it satisfies an inequality. Okay? So example one says determine whether each ordered pair is a solution to the inequality 3x minus 5y is -12. So we want to take that inequality, anywhere we see an x for part A, we're going to plug in a 2, and for part A for y, we're going to plug in a -3. So I would get 3 times x, which is 2, minus 5 times y, which is -3, and I want to see if that is greater than or equal to -12. Well, we've got to do a little work here. We need to multiply and then add and see if whatever we get on the left is greater than or equal to -12. So 3 times 2 is 6. -5 times -3. Well, two negatives become a positive, so that's going to be plus 15. And we want to know, is that greater than or equal to -12? Well, 6 plus 15 is 21. And 21 is certainly greater than -12. So we would say yes, this ordered pair is part of the solution set. The solution set is vast. It's going to have infinitely many ordered pairs, but one of those very specific ordered pairs is going to be 2, -3. Okay? Let's see what else we have. So for part B, we have the ordered pair 2, 8. So we're going to replace our x in the inequality with a 2, the y with an 8, and we're going to see what we get. So we get 3 times x, which is 2, minus 5 times y, which is 8. And we need to know, is that greater than or equal to -12? Well, 3 times 2 is still 6. That hasn't changed. -5 times 8. Well, -5 we're going to treat like a negative. Negative times a positive is negative. 5 times 8 is 40, so that's going to be -40. And we need to know, is that greater than or equal to negative 12? Well, 6 minus 40 is negative 34. And if I'm thinking about negative 34 and negative 12, the further away you are from 0 on the negative side, the smaller you are. The further away from 0 on the positive side, the bigger you are. Since both of these numbers are negative, I need to look to the left of the number line. And negative 34 is much further away from 0 than negative 12. So this is not true. This is false. So here I would say, no, this is not part of the solution set. Okay, last up, we have the ordered pair 0, 0. So we're going to plug in 0 for x and y. So I get 3 times 0 minus 5 times 0. Is that greater than or equal to negative 12? So 3 times 0 is just 0. 5 times 0 is 0. 0 minus 0 is just 0. So is 0 greater than or equal to negative 12? Yes, this is absolutely true. So we would say 0, 0 is part of our solution set, okay? So understanding how to just test a point is going to be important because when we start graphing these inequalities, one of the things we have to do is just kind of throw in a test point to make sure we're good. So understanding this is going to be important very, very soon.